So last time, where are we at? Well, we talked about sums, infinite sums. We call them series. And we were able to look at a couple of special cases. Namely, we had geometric series and telescoping series. And we can actually find the answers for those cases. But a lot of time we can't find an answer explicitly. We'll just be satisfied to know that there is an answer. So that's where we're going next. We want to develop our tools to decide, is there an answer? So let's start with a really simple observation. So let's suppose that the sum converges. In other words, we can find an answer. The claim is that if I look at an individual term, it has to go to 0. Now, why is that? Well, if you think about what's happening here, so remember, this is our partial sums. And we're writing it in a slightly different way. Now, normally the way we would write this before is it says, look, if you want to find the nth partial sum, what you do is you start with the n-1 partial sum, and then you add one more term. Because to get to the next partial sum, you just add the last term. So if you move this across, you get that the last term is the difference of two partial sums. Now, we say that the sum is converging, which means that this partial sum converges to L, and that partial sum is converging to L, so it's converging to L minus L, which is 0. All right. So, if the sum converges, the terms have to go to 0. Now what you can do is you can flip that around. There's a fancy word for this. It's called the contrapositive. But just think of, says, look, flip the order, but do the opposite. So, what's the opposite of having the limit go to 0? Well, the limit doesn't go to 0. What's the opposite of the sum converges? The sum diverges. So the conclusion is, if the limit does not go to 0, then the sum diverges. Okay, that's a pretty straightforward, easy idea. Now, a word of warning, because a lot of people will hear this statement and they'll start to implicitly say, aha, if the limit if the limit doesn't go to 0, sum diverges. Maybe if the limit does go to 0, does that imply converges? And the answer is no, it does not. And we'll do an explicit example of that in just a moment here. So be careful. It's important to understand what things say, but also what they don't say. And we want to make sure we understand what they say. That's our goal. All right, so here we have some examples. So what can we say about the following series used in the nth term test? So the sum, n equals 1 to infinity, of n. Okay, well that's 1 plus 2 plus 3 plus 4. Okay, all right, what's going on? Well, the nth term, see this, that is our a sub n. So the question we're asking is what's happening to a sub n? So the limit as n goes to infinity of n. Well, we don't even need to know what it goes to. The question is, does it go to 0? The answer is no. It definitely does not go to 0. It gets huge. It's actually infinity. But we don't even need to know that it's infinity. We just need it to know, not 0. All right. Well, the next one. Sum n equals 1 to infinity of minus 1 to the n. And, oh dear, this is wrong. Let's fix that. Okay, now we're okay. Now, you might say, what was wrong? Well, notice, if n equals 1, you should have minus 1 to the 1. So the first term should be a minus 1, not a plus 1. Oops. All right, well, easy fix. In fact, I think we'll fix this one too. All right. So, what's happening? Well, we have 1, minus 1, plus 1, minus 1, plus 1, minus 1, da 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 da. So, the question is, what happens here? So this is our a sub n. So, what's the limit as n goes to infinity of minus 1 to the n? And we should have, by the way, here said our conclusion is this implies that the sum diverges. We can even be more precise. It diverges to infinity. It's infinite. Now, limit as n goes to infinity minus 1 to the n. Well, it's not 0. In fact, it's not anything, because it alternates. Plus 1, minus 1, plus 1, minus 1, plus 1, minus 1. So, since it doesn't go to 0, then that implies that this sum diverges. Now, this is a little bit different behavior. See, up here we said it's going to head off to infinity. Here, it doesn't go to anything in particular. It just oscillates. In fact, you can sort of see what happens. So you start with just 1, then 0, then back to 1, then back to 0, then 1, then 0, and it's just going to keep doing that. All right, last one. Sum n equals 0 to infinity of minus a half to the n. So that's 1, then minus a half, because that's minus half to the 1, plus a quarter, because that's minus half squared, minus an eighth, plus a 16th, so forth, and so on. All right. So that is our nth term. That's our a sub n. So what's the limit as n goes to infinity of minus 1/2 to the n? Well, the answer is 0, right? Because it's a small number. When you raise a small number to n, that's going to get very, very small. And the limit goes to 0. Now, what's the conclusion? Because remember, what are we using? We're using the nth term test. So, when it doesn't go to 0, our conclusion is diverges. When it does go to 0, our conclusion is unknown. That's what we have. By the nth term test. Now, does that mean we give up? No. It means we start looking at other tools. Now, right now, we don't have very many tools. But in this case, we say, wait a second, this isn't just any sum. It's a geometric sum. And in fact, it's a geometric sum. And here, the r in absolute value is less than 1. So, because it's geometric, we can actually make a conclusion. Namely, we can conclude that this does converge. And not only does it converge, we can say what it converges to. And it converges to, the first term is 1. So 1 over 1 minus. And the thing we multiply at every stage is minus a half. So that's minus minus makes a plus. 1 plus a half is 3 halves, so 1 over 3 halves, which becomes 2/3. So that's what it does converge to. But if we only are using the nth term test, no conclusion. We don't know. Not enough information. All right, well, let's start with a very famous sum. And it even has a name, so it must be famous. This is called the harmonic sum. And what is it? Well, you start from 1 to infinity of 1 over n. So you get 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over 4 and so forth. All these things. Now, let's use our nth term test. So, the nth term test, what does that allow us to say? Well, what we do is we look at the limit as n goes to infinity of the nth term, which is 1 over n. Well, what does that do? It gets very small, so it equals 0. All right, conclusion? Well, that implies we don't know. Okay, so at this point we can't make a conclusion just from the nth term test. Well, but maybe there's something else we can use to help us make a decision. So you'll notice that we've done some grouping here. So the 1 is by itself a half. Well, all right, we can say certainly that's a half, because a half is a half. Now notice the next terms, a third plus a fourth. Which one is the smaller term? Is it the third or is it the fourth? The third, well, that has a smaller number downstairs. Does that make it the smaller value? No. It's the fourth. Fourth is the smaller one. Now, so let's suppose I replace the third here by fourth. So I could certainly say that this part is greater than a fourth plus a fourth, which is a half. Okay, let's go to the next grouping here. A fifth, a sixth, a seventh, an eighth. Which one's the smallest? It's the eighth. So if I replace each one of these by the smallest one, then I'll certainly make the whole expression smaller. So this is bigger than an eighth plus an eighth plus an eighth plus an eighth. Well, how many eighths do we have? That's 4 eighths, which is a half. Now you're probably seeing where we're going here. See this next big block? Well, what can we do? Well, let's replace all the terms by the smallest term. That's the 16th. So there's a 16th from the 1/9, a 16th from the 1/10, from the 1/11, the 1/12, the 1/13, the 1/14, the 1/15, and the 1/16 just stays as 1/16. And if you count, there's going to be 8 of them. So that's a half. Now, can we keep it going? Yeah, we can. So 1/17 up to where? Where do we make the next cutoff at? Can you see it? Where are cutoffs happening? 2, 4, 8, 16. The next one, 32. And here, if you now replace everything in this block by 1/32, what you'll get, this is bigger than 1/32, added up 16 times, which is a half. And we can keep this going forever. So what does that tell us about our sum? This says that the sum from n equals 1 to infinity of 1/n is bigger than 1 plus a half from the first block, plus a half from the second block, plus a half from the third block. And in fact, each one of these blocks is at least as big as a half. Of course, the length of the blocks gets bigger and bigger, but the thing is, there's a lot of room in infinity. So even though the blocks themselves are getting bigger and bigger, there's still plenty of blocks left. So we're going to have enough space. So in fact, it's bigger than 1 plus a half added up infinitely often. Well, what happens if you add up a half infinitely often? Well, the answer is you get big. It's infinity. So the sum is bigger than infinity. Well, there aren't that many things which are bigger than infinity. In fact, there's really nothing above infinity. So we come to the conclusion that the original sum, the sum, n equals 1 to infinity of 1/n, is infinite. All right, good. Now this is a very famous series. In fact, we're going to put a box around that. Now if you remember, whenever you see a box around something, that's a sign that we should pay attention to this formula, because it's probably going to show up multiple times in the future. And the more that we see it, then the better we're going to get at using it. Now, we have some space left and some time. I'll just mention a few things here. It illustrates, by the way, why you have to be careful with the nth term test. Just because something is going to 0, the nth terms are going to 0, does not mean when you add everything up, it's going to be finite. It might be that things are going to 0, but they're going to 0 too slowly. See, here we have the 1/n. That's going to 0 in some sense in a very slow way. So it's getting there, but it's taking its time. If you compare that to something we had a moment ago, see, minus a half to the n, that also goes to 0, but in some sense, it's going to 0 a lot faster. If you put in n equals 100, the number you get is super, super small. So small that your calculator probably will say it's 0. If you put in n equals 100 here, the number you're going to get is not that small. So somehow, there's always a question about, okay, how quickly do you go to 0, and do you go to 0 fast enough? Now there's another thing, and when I was a student, back in the day, a long, long time ago. And, well, our college had this, for Valentine's Day, you could print a little tiny message to your sweetheart. And it could be sort of they call it a love line. And I thought, you know what, it would be fun to do something kind of mathy, right? Because I'm a math person. I was a math person back then too. Still am a math person. And so I wrote the following. And it said, my love for you. See, I'm romantic. I used the word love. My love for you is like the harmonic sum. And why is that? Well, growing little by little, but infinite in the total. Oh my gosh. See, if you need to, you can borrow this line. It's okay. I don't mind. You can use this to woo a very math-oriented person. Because they'll say, that is like the harmonic sum. See, it does grow slowly because the terms are going to zero, but when you add them all up, it's infinite. What a beautiful line. All right, good. So, now we're going to move into another test. So we have the nth term test. We're going to add another test. And this is the integral test, which means all those fun things we learned about integrals are still useful to know. So it says the following. Suppose f of x is continuous, positive, and decreasing. So in other words, f is a nice function. So if we have our sum of f of n, and we look at that, and we have the integral of f of x dx, and we look at that, they both converge or they both diverge. So in other words, we can connect the behaviors together. Now, why do we care about this? Well, finding sums is tough, very, very challenging. But finding integrals is tough, but we have tools. See, the integration is in the continuous world. And there's better tools for that. Now, why is this true? Well, when we think of this sum, we really can think of this like, okay, we're adding up sort of discrete things. So one way we can think of it is we can think of it as we call it a Riemann sum. And so that is, we're going to think of it as a bunch of rectangles. So we're going to have two areas. One area is a bunch of rectangles that represents the sum, and the other area is what comes from the function. And we're going to say, okay, look, what happens? So one way I can do it is I can think about, suppose this is k, and then I keep going. Now one thing I can do is for k, I can have it go up and to the left. I can just do it at every stage. And if I do that, I get a bunch of rectangles, and you can see the areas, add them up. And the rectangles, where are they? They're all underneath the curve. Now the other thing I could do is I could go to k, and I could go not to the left, I could go to the right. I can do that at every single one. And again, a bunch of rectangles, and the function. Now, what's the story? Well, the claim is if one converges, the other converges. So let's suppose that we know that this sum converges. So that has finite area. Well, now let's come to this picture. Look at the area. The area underneath the curve, which is the integral, is smaller than the area that comes from adding that up. So smaller area, if this is finite, that is finite. Now, if the integral is finite, then use the other picture. It says, look, the integral, that says there's finite area underneath this curve. And here, we can add up these. That's also going to be a finite area. What about diverging? Well, let's suppose the integral diverges. Well, now come to this picture. If the integral diverges, that means that the area underneath this curve is infinite. And by the way, it's the tail that you worry about. You don't worry about the start, it's the tail. But now, look at the rectangles. The rectangles have more area than the curve. So, if the curve has infinite area, the rectangles also have infinite area. So it diverges. Similar, you can go over here. So that's what the integral test says. It says, hey, I can think of these as being tied together. But actually, the integral test, there's a little side note here, and I think it's worth mentioning. So even though we know things converge or diverge, there's always the question of, well, what do I do if I want to get a good estimate? And so a reasonable test should help us understand how do we get a good estimate. So that happens here with the integral test. So there's a way to get a good estimate, and here's what you do. So you may want to say, how much is my error? Because I'm not going to add up infinitely many things, but maybe I say, do I need to add up 100 things? Do I need to add up 1,000 things? How many things do I need to add up before I get a good estimate? And here's the intuition. So if I have the sum, it's from, say, n equals k to infinity of my f of n, well, that's approximately the sum from n equals k up to some capital N of f of n plus an error. In fact, we can replace that approximately. That's equal, right? Now, the question, of course, is what can we say about the error? And here's the beautiful thing. The error is less than or equal to the integral from capital N to infinity of f of x dx. Now, why is that? Well, here's sort of the intuition. So you have this function going down, and you've added up a bunch of rectangles, and you've added up to some point here. Okay, so what's happening? You see, the error, really, that's the sum from n equals capital N plus 1 to infinity of f of n. That's our error. Okay? That's not very surprising. See, if you add those up, that's what you get. So, what do we say? Well, here's capital N. So you go to n plus 1, n plus 2, so forth and so on, and you make your rectangles. And the way you do it is you go up and to the left. And you're going to do that all the way down. So forth and so on. Now, if you add up from n plus 1 to infinity, f of n, that's these rectangles here. And that's smaller than the integral from capital N to infinity of f of x dx. So, you can always figure out how far do I have to go. You just say, look, how far do I have to go to make this part of the integral small? So that's a way that we can be confident that we say, look, if we stop after 1,000 terms, the rest of the value is at most this. And so that gives us a way to get an error. Because look, an estimate is only as good as your error. If you have a huge error, it's a terrible estimate. If you have a small error, it's a good estimate. So it's good to know things. All right, well, that's a little aside. Let's ask a question. Does the sum from 0 to infinity of 1 over n squared plus 1 converge? Now, if you use the nth term test, we can see that it goes to 0 because it's 1 over a big number. Okay, so by the nth term test, we don't know. All right, but we have a better test. So what we can think of this here as being is we can think of this like, well, this is f of n, where f of x is what? Well, think of this as where you see an n, put an x. So it's 1 over x squared plus 1. And now we're going to ask the question, okay, well, I can say, look, this sum from n equals 0 to infinity of 1 over n squared plus 1 is somehow tied to the integral 0 to infinity of 1 over x squared plus 1. So, if I'm having a hard time with that sum, I ask, okay, can I have a hard time with this integral? I'm going to just pause for a second and say, if you're ever worried about the start, because notice there is some technical things you need to be positive and decreasing, and it might not be positive and decreasing at the start. You don't care about the start. Remember, when we're talking about converge, diverge, we always wonder about what happens at the end, the infinity. That's the important part. So it's the tail that tells the story. So now let's work on this integral. So integral 0 to infinity of 1 over x squared plus 1 dx. This sounds familiar, like we've heard of this integral somewhere before. What do you think? Does it? Well, well, I think we have. That's arctangent. Arctangent, you beautiful function. It's been too long. All right, so it's arctangent of x from 0 to infinity. Now, of course, you can't plug in infinity, so when we talk about arctangent of infinity, what do we mean? Well, we mean, what happens to arctangent of x as x goes to infinity? Well, what does happen to arctangent of x as x goes to infinity? The answer is it goes to pi over 2. Subtract arctangent of 0 is 0. Now, do we care about the value? No. What do we care about? The question is, does this converge? In other words, is it finite? Well, it does turn out that pi over 2 is in fact finite. It's less than infinity. Hard to believe, but true. Well, maybe it's not so hard to believe. So, what does that say? That says that this integral, we know, converges. We just checked it. So, that says, because they're tied together, that the sum converges. Now, does the sum converge to pi over 2? No, not even close. Well, why not? Well, you can actually see it if you think about the pictures here. Because if you look, because of the way the pictures work, you can see that there's little bits of error. It's these little tiny pieces. And these little tiny pieces, they're small. So, I mean, pi over 2 is not a bad estimate. But still, the moral is the difference between these is contained in how much area there is between the curve and these little pieces of rectangle. So we are not claiming that the 1 over n squared plus 1 goes to pi over 2. That is not true. But we can claim it goes to something, it does converge, and you can always find it numerically pretty well. It turns out that with more sophisticated tools, it is actually possible to get an explicit value for this, but that's outside the scope of our class. All right, well, now that we have the integral test, we're going to look at a very important test, and that is p-series. So, we're going to look at the sum of 1 over n to the p. This is a very famous series. In fact, this actually has a name in mathematics. This is known as the zeta function. And I apologize, my zetas tend to look like psi sometimes. This is called zeta of p. And so famous, there's actually $1 million question tied to understanding this series. So, all right, does this converge? Does it not converge? All right, so what can we do? Well, we want to figure out for which p does the sum 1 over p converge. So what we do is we say, look, the sum, we're going to connect it to the integral. So we need to ask ourselves the question, when does the integral 1 to infinity of, what's our function? Well, look, n, that's our index. So n is becoming our x. So it's 1 over x to the power p dx. All right. So if I want to know when does this sum converge, I ask when does this integral converge. All right. Now 1 over x to p, you got to be a little bit careful here because there's two cases. So we do those. One case is p equals 1. Now, when p equals 1, you get the integral 1 to infinity of 1 over x. Now, what's the integral of 1 over x? It is natural log of x. And we go from 1 to infinity. Now, what happens to natural log as x goes to infinity? The answer is it gets huge. It does it very slowly. You know, log, it drags its heels. I don't want to get big. I want to stay small. And it doesn't want to go arbitrarily large. But it does. It does. It takes its time, but it gets there. Now you might say, hey, you forgot to subtract that. Yeah, it doesn't matter. Natural log of 1 is 0, but it doesn't matter. Once you're infinity, it's hard to recover. So that tells us it definitely is not going to work when p equals 1. Well, that doesn't surprise us, right? Because remember, what happens when p equals 1? That's the sum of 1 over n. That's the harmonic sum. And we already know that it's going to diverge when it's p equals 1. Okay, so that agrees with what we've seen before. All right, well, what if p is not 1? Well, then the way we should think about the integral is we should think of it as x to the power minus p dx, because that's sort of the better way to write it, because our other rule is we're thinking of like x to a power. Now, how do we integrate that? Well, the rule is you add 1 to the exponent, so that's x to the power minus p plus 1, and then you divide by that new exponent. So 1 over minus p plus 1, and you go from 1 to infinity. Now, the 1 doesn't matter. It's the infinity, the tail. What's happening at the tail? That's going to be what dictates the story. So, let's think about it. So there's a couple of cases. And here, the 1 over minus p plus 1, that's a constant. So you're getting a huge number raised to the power of minus p plus 1. Now, if minus p plus 1 is a positive number, then you're getting a huge number raised to a positive exponent. That's going to be big, right? Because a big number, positive exponent, like, you know, n to the power half, n to the power 3. It's big, 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 big. Now, what happens if minus p plus 1 is less than 0? That means it's a negative exponent, which really means it's downstairs. So it's a huge number downstairs. So that's going to be a finite number. Now technically, I'm not going to, that's just the one end, right? We can even say what it is. It's going to go to 0 minus, and then when you plug in 1, 1 over 1 minus p. Okay? So that's what we mean. But again, we don't care about what the value is. We care about whether it's finite or not. So, let's rearrange this. So here, I could say, instead of minus p plus 1 is greater than 0, I could say, well, if p is less than 1, because that's what that would say. And here, this would say if p is greater than 1. So, putting this together, p equals 1 diverges. P less than 1 diverges. P greater than 1 converges. So the integral, this converges when p is greater than 1. Now, this is important. You know it's important because it even has a name. So we're going to keep referring back to this over and over again. P series. And it's kind of an interesting thing, because what does this say? Well, this says, look, if you have the sum, n equals 1 to infinity, of 1 over n, well, that's diverging. But what if you have the sum, n equals 1 to infinity, of 1 over n to the 1.000000001? What happens? It converges. So somehow it's like this 1 over n is like just barely short, because these two, they're very, very close, especially for the first, couple million terms. you wouldn't be able to really distinguish anything. But somehow, in the long term, see, the long-term behavior, that's where the interesting things happen. So we're going to keep seeing p series over and over again. So the thing to remember is that if you have 1 over n to the p, you look at that p. If p is greater than 1, converges. P less than or equal to 1, diverges. And you're done. And it's good to know that. On a side note, I mentioned this was a famous sum, and it has been studied. So I'll give you an example. If you add up the sum, n equals 1 to infinity, of 1 over n squared, it's known exactly what that is. That's equal to pi squared over 6, right? Well, I don't know. It's equal to something, right? It's kind of like, pi? Really? Yeah, it really is a pi. Wow, weird. But it gets even stranger. Now, if you add up 1 over n to the 4th, that's also known, and I don't know off the top of my head, but it is known. But what if you add up 1 over n cubed? Well, what is that? Well, the answer, we're not exactly sure. Now, when I say we're not exactly sure, we can approximate that to, 1,000,000 digits. That's not a problem. The problem is, does this equal something fancy like pi squared over 6? It's not known. We don't know. There's a lot of things we don't know. And you might think that, wow, I thought math had all the answers. No, not yet. Isn't it great? Isn't it wonderful? There's still things we don't know. Ah, what a great time to be alive. All right, let's do another problem. Show that for 0 less than r less than 1, that this sum, n r to the n, converges. All right, cool. Well, let's think about that. So, what do we have? N r to the n. Now, r is small, so there's a couple of things that are nice about this. First off, that means that these are positive. Now, you might say, okay, is it decreasing? Well, got to be careful there. Because what are we going to do? We're going to really think about this as the integral test. So the function, we're going to think of this as x r to the x power. Is this function decreasing? The answer is eventually yes. What happens though is at the start it goes up, but eventually it goes down. Now, because it's increasing at the start, you might say, well, the integral test can't be used. But remember, the integral test says, I only care about the end. So, don't worry about the start. Worry about the end. So we'll say, look, because in the end, it does decrease down to 0, we can use the integral test. So, let's use the integral test. And what do we get? Well, we have that we want to look at the integral from 0 to infinity of x r to the x dx. Because what we're doing is we're replacing our n's by x's, so we're thinking this is our function. Now, how do we integrate this? Well, it might help to recall things. First off, let's recall the integral of r to the x. What is that integral? Now you might say e to the x is really easy, right? E to the x is e to the x. Well, what's the integral of r to the x? Well, if you don't remember, here's how you can rederive it. You want to have something that looks like e to something. So, can we replace r by something that looks like e to something? And we can. It's e to the natural log of r to the x. Or, if you like, that's e to the log of r times x dx. So it's like e to a constant x. So the way you integrate e to a constant x is you have e to that constant times x divided by your constant. And then you throw in a plus c, of course, because you always want to make sure you get all the points. E to the natural log of r times x, well, work backwards. That's r to the x. So you get 1 over natural log of r times r to the x. Okay, so that's the integral of r to the x. How do you integrate x r to the x? it seems that this is something that has multiple parts, right? There's x, there's r to the x. How would we do integration in that setting? Well, we can do integration by parts. All right, so if we do integration by parts, we say, all right, we have two pieces. Which part do we integrate? Which part do we differentiate? Well, the r to the x essentially is going to look like r to the x. Now that's whether you integrate or differentiate. The x, you want to make that simpler. If you integrate, that becomes essentially x squared. More complicated. Differentiate, 1. That's beautiful. So we'll make this part be the part we differentiate, this part the part we integrate. So that du is equal to 1 dx, and then the integral of r to the x, we just did that. That's 1 over natural log of r times r to the x. So we get uv 1 over natural log of r, x, r to the x, evaluate that from 0 to infinity, minus the integral of v du. So that 1 over log r is a constant, I can pull it out. So 1 over log r, integral r to the x dx. Now here, when you plug things in infinity, what wins between polynomial and exponential? And the exponential, by the way, exponential decay. Well, the answer is the exponential decay beats out. So polynomials grow slower than exponentials. So when you go to infinity, that goes to 0. Well, that's when you plug in 0. Well, you get 0 times something. So this part is 0. Okay, that's good. What's happening over here? Well, whoops, forgot the bound, 0 to infinity. All right. Well, so we integrate that again. So minus 1 over natural log of r. Then integral of r to the x, there's another 1 over natural log of r times r to the x from 0 to infinity. And what do we have? Well, when you go to infinity, these terms at the start are constants. You get r raised to a huge power. That's going to go to 0. So you're going to get 0, subtract, you plug in 0, r to 0 is 1. So subtract minus 1 over log r times 1 over log r. Now, this turns out to be 1 over natural log of r squared. Do we care about the value? No, not really. What do we care about? We care about, is it finite? And yeah, this is definitely finite. What does that tell us? It tells us the integral converges. But remember, the integral test says these things have the same behavior. And therefore, the conclusion is, so you can say, so by integral test, since the integral converges, then the sum converges. And that's the conclusion. All right, so there we go. Now we know it converges. But we don't know what it converges to. We don't know that. Because that's, remember, the integral test doesn't say what things converge to. See, like this 1 over n squared, the integral of 1 over x squared, you wouldn't ever get a pi squared over 6 out. So there's some sort of, there's a gap there. So we don't know what it converges to. That would be a very different type of a question. So let's go to the next question. What does it converge to? Oh, okay, all right. Well, Now, like I said, different type of a question. We can't use the integral test to find what things converge to. We can't use the nth term test. When we talk about convergence test, they're only useful to give us yes/no answers. Does it converge? Does it not converge? Yes or no. So when it says find something, you have to use other tools. So let's think about what we're looking for. So we're going to want to find the sum n times r to the n for absolute value of r less than 1. We want to figure out what that equals. So let's think about what the sum looks like. So the sum, n equals 0 to infinity, of n r to the n, I can think of it in the following way. Well, that's 0 times r to the 0. All right, well, that's not too surprising. plus 1 times r to the 1 plus 2 times r to the 2 plus 3 times r to the 3 plus 4r to the 4 plus 5r to the 5 plus 6r to the 6, and so forth and so on. Now, all right, what do we do? So we want to find these sums. So the problem is that this is not just a geometric. If there wasn't the n at the start, if it's just r to the n, life is good. Geometric, we're done. But it's not. That extra n throws a little bit of a wrench into our process. But here's sort of an idea. Let's think of it as the following. Look, I've got a single r. How many r squares do I have? Well, I have 2. So I'm going to think of it as r squared, and then I'm going to start another sum in r squared. All right. How many r cubes do I have? Well, I have 3 of them, so I'm going to have an r cubed. I'm going to put an r cubed here, and then, well, I still have 1 to go. I'll put another r cubed there. How about r to the 4ths? Well, I've got 4 of them. So r to the 4th, and r to the 4th, and r to the 4th, and then I need to start a new one, r to the 4th. How about r to the 5th? Well, all right, I'll do that. I'll break things up as r to the 5th. Now, why am I doing this? Well, I'm doing this because I want to reduce to something I already know about. What do I already know about? I already know about geometric sums. So what I'm trying to do is I'm trying to make things look like geometric sums. And I'm trying to find ways to break things up into nice little pieces. And you'll see what's happening here. Well, one thing that's happening is we're getting a lot of terms. But one of the things we can think about this as being here is we can really think about, what do we really have here? Is we can think of each line here as being its own geometric sum. Because that's really, if you look at every single line, that's what's happening, right? Because you have r squared, r cubed, r to the 4th, so forth, so on. Here, it's a geometric sum. The first term is r, and every time you multiply by r. Here there's a geometric sum. First term is r squared. Every time you multiply by r. Here, geometric sum. First term is r cubed, multiplied by r. Now, let's add these up. So what are we doing? Well, we're saying, look, instead of trying to find one sum, we're going to add up infinitely many infinite sums. So, wow, okay, let's see what we get. Now, remember the rule. If you have a geometric sum, you start with the first term. So for the first one, we're going to get r, and then you divide it by 1 minus what you multiply by. Every time here, we're multiplying by 1 minus r, right? So every time we multiply by r, so it's divided by 1 minus r. If we go to the next line, our first term is r squared. What do we divide by? Well, we look at what we multiply. See, every time we multiply by r, so again, 1 minus r. The third line, it's geometric. First term is r cubed, so we're going to get r cubed divided by 1 minus r. Fourth line, first term is r to the 4th, so r to the 4th divided by 1 minus r, and that continues. So, if we look at these individual sums, that's what we get. Now, remember, that's not our answer. We now need to add all these up. So, we need to add up r over 1 minus r plus r squared over 1 minus r plus r cubed over 1 minus r plus r to the 4th over 1 minus r plus r to the 5th over 1 minus r. Now, what kind of sum do we have here? It's geometric, right? Because our first term is r over 1 minus r. To get to our next term, multiply by r. Get to the next term after that, multiply by r. And every time we multiply by r. So, we take our first term, divide that by 1 minus what we multiply by. And therefore, we get r over, you bring that upstairs, 1 minus r squared. So that's our conclusion. We have that our sum is r, divide that by 1 minus r quantity squared. Now, that's, not so obvious what to do or how to begin. But I want to say that within a couple of weeks from now, we're going to get to the stage where we feel comfortable with this. This is actually going to be a fun problem for us to do in a few weeks. So expect to see something like this again in the near future. But not today, because we're done for today. And we'll see you again next time. Have a good day. Bye.